the last section is three-phase, and that's used for commercial motors. And for that, we've got VA, VB, and VC. Out of curiosity, how many of you guys have worked with wiring houses? It seems from Aiden's comment, yeah, that at least Aiden has. Okay, so Aiden, did you work with three-phase at all?
Yes, sir. We did a storage building that had a three-phase panel.
Oh, awesome. All right. So this is a story with this. VA is black. VB is red. VC is white. Man, I didn't like the way that came out. VA is 120 at an angle of 0 volts RMS, and that's black. VB is 120 at 120 degrees RMS. It's unfortunate that the degrees happens to be the same as the voltage. And VC is at minus 120 degrees. Now, in single phase, we took our power between our hot and our neutral. In dual phase, we took our power between our VA and our VB for the heavy current drawing appliances, but for the light current drawing appliances, for those 15 and 20 amp circuits, we took it between either VA and V neutral or VB and V neutral, depending if it was a high powered or depending upon if it was a high power when we use this, or low power where we use these. Three phase, we take it between VA, VB, also between VB, VC, and also between VA and VC, and we take them all and all equally. And it's easiest to see what's going on if we draw the phasor diagram. Here's our VA. There's our VB. And there's our VC. So 0 degrees, 120 degrees, minus 120 degrees. This is 120 volts, 120 volts, 120 volts, all RMS. The reason why we have this three-phase, the reason why three-phase is so important has to do with motors. If you've got a simple magnet and you rotate it on a fulcrum so it can spin freely, you've got one electromagnet here. Let me shift the way I draw this. If you've got one electromagnet here, one electromagnet here, and one electromagnet here. So there are 120 degree phase differences between the electromagnets. Then if you drive these three electromagnets 120 degrees out of phase, not only will the magnet spin around its axis, but its torque will be completely constant at every angular rotation. And this is very different than if you've just got two coils or 4 coils, in which case you'll have a varying degree of torque. But with 3, you've got a perfectly even amount of torque. The only question is how do we, and that's why three-phase is so important, because it lets us create these high-powered electric motors that have perfectly even torque curves. There is a problem though. How do we wire VA, VB? I've got my little phasor notation. How do we wire this VA, VB, VC to these electromagnets? I mean, it's pretty clear that one side is going to be VA. Let's see. VB and VC. But what do we do with the other side? We'd like to wire it to neutral, but there's no neutral. Any ideas what we can do? Aiden, you might know. What's the vector sum of VA plus VB plus VC? Just look at these vectors. John, we're up to you. What's if you do vector addition between VA, VB, and VC, if you add those three up, what will you get?
Is it just going to be 120 times 3? Right?
Well, I think you're, no. If you multiplied the magnitudes together, you'll get 120 times 3. But that's different than if you, that would be if you add the apparent power, say. But that's different than adding the phasors. So this is a phasor. Do you remember how to add phasors? You put them head to tail. So if you add VA to VB to VC, do you want to try it again? Or do you need another hint?
So then it would be... So I understand the head to tail part, and so
Yep.
the head of the
So
tail
put
of
this.
VA would, okay.
So I'm going to redraw VB, but I'm just going to shift it to the right.
Mm-hmm.
And now can you put in your VC? Here's your VC. I'm just going to shift it
into the triangle.
So now what happens when you add them together? Where do you end up with?
Back to the origin of it all.
Back to the origin, back to 0. So you don't need to have a neutral with 3-phase, because all you need to do is just add up your 3 phases anytime you want to, and you've created a neutral. They call that a virtual neutral, and it saves you an extra wire. So we could have an extra wire just going around all this, and we're going to attach our outputs to that wire. And now we've got our circuit. Only with 3 wires, we can power very powerful electric motors, and we get perfectly even torque curves. So this is the reason why 3-phase power is so important. One thing that's different about 3-phase power is that even though the magnitudes of each voltage vector are 120, you can't get to those with a digital multimeter. When you had single phase, you could put one side on the neutral, one side on the hot, and you'd read 120. When you had dual phase, you could put one side on the neutral, the other side on VA, VB, you'd get 120. Put in between VA, VB, you'd get 240. But with 3-phase, all you have access to are these 3 points at VA, VB, VC. You don't have access to a neutral wire because there is no neutral wire. Unless you break into a load like we did on our right. But actually coming into the house, there is no neutral wire. So if you were to use your digital multimeter to verify that you've got 3-phase power, the only way that you could do it is to measure your leg-to-leg voltages. So as an example, this particular leg-to-leg is VAC. One side on your C terminal, one side on your A terminal. And to see what you'll get, it would be your A terminal subtracted from your C terminal. That gives you a triangle. With a little bit of algebra, you could do it, but I'll do the algebra for you. It turns out to have a square root of 3 in there. And it also has an angle. The angle is less important. You can see the angle is 30. It's that little angle is 30. But the most important thing is this 120 square root of 3. That works out to be about 207 volts RMS. And so that is your leg to leg voltage. So you put a digital multimeter between any two legs and you'll read 207 volts. They'll just be at slightly different angles. You can see that this angle is 180 degrees, and I won't draw it, but your last angle is at, if this is at 150 degrees. They're all separated from each other by 120 degrees. So they're all separated by 120 degrees. Did I say 180? Man, let me try that again. This is 90 degrees. And then 90 plus 180 gives you your other leg to leg, and 90 minus 180 gives you your other leg to leg. So your V leg to leg for a 3-phase is always going to be 207 volts RMS at some angle. And that angle will be either 30 degrees or minus 90 degrees or minus 210 degrees. Possibly plus 180 degrees, depending upon if you flip your leads, you'll just add 180 degrees phase shift. All right. Any questions on single phase, dual phase, or 3-phase?